The morning mist hung low over Yokosuka Naval Arsenal on the 17th of July, 1944, as a team of Japanese engineers gathered around something that had become increasingly rare in the third year of the Pacific War. An intact enemy fighter, not wreckage scattered across a reef or the charred skeleton of a crashed aircraft, but a complete, relatively undamaged Grumman F6F Hellcat that had been captured after an emergency landing on a Japanese-held airfield. The fighter sat under the harsh lights of the hangar, its broad wings still folded back against the fuselage in the configuration American deck crews used to pack more aircraft onto their carriers. For the engineers surrounding it, this wasn't just another captured enemy machine. It was a window into why Japanese pilots were dying at rates that made the losses at Midway look modest by comparison. Since August of 1943, when Hellcats first appeared in significant numbers, American naval aviators had been systematically destroying Japanese air power. The kill ratios being reported from the front were almost impossible to believe. 19-1. For every Hellcat lost, 19 Japanese aircraft were being shot down. The engineers knew these numbers. They'd read the combat reports, interviewed the surviving pilots, analyzed the fragmentary intelligence that made its way back to the home islands. What they needed now was to understand the machine itself, to measure it, weigh it, disassemble it, and discover exactly what made it so devastatingly effective against fighters that had ruled the Pacific skies just 2 years earlier. Commander Nakamura Hiroshi, the senior aeronautical engineer assigned to the evaluation, walked slowly around the Hellcat that first morning. He'd spent the previous decade designing fighters for the Imperial Japanese Navy. He understood the philosophy that had guided Japanese aviation. Lightness equals agility. Agility equals victory. Strip away everything that isn't essential to maneuverability and range. Armor is dead weight. Heavy armament slows you down. A skilled pilot doesn't need protection because he won't get hit. That philosophy had produced the Mitsubishi A6M0, and for a brief window it had seemed vindicated. But now, as Nakamura examined this captured American fighter, he was looking at the physical embodiment of a completely opposite design philosophy. The Hellcat was massive. It dwarfed the Zero in every dimension. The wings alone seemed to contain more metal than an entire Japanese fighter. Begin with the wing fold mechanism, Nakamura instructed his team. I want to understand how they're achieving this. The Hellcat's wings were still folded when they'd captured it, which meant the engineers could examine Grumman's patented Sto-Wing system in detail. They'd seen wing folding mechanisms before. The Zero had folding wingtips designed for elevator access on carriers, but those were simple hinges at the very edge of the wing. This was something entirely different. The outer wing panels didn't fold up like you'd close a book. Instead, they rotated backward along a skewed axis, twisting as they moved until they lay flat against the rear fuselage. One of the junior engineers had brought photographs of American carriers taken by reconnaissance aircraft. The images showed deck crews folding and unfolding Hellcat wings with what looked like remarkable speed. No elaborate rigging, no teams of men struggling with the weight. Just a couple of sailors per wing, moving panels that must weigh hundreds of pounds as if they were garden gates. This mechanism shouldn't work, one engineer muttered as they examined the pivot assembly. The entire wing's structural load, everything that kept it from tearing away during high-speed maneuvers, was being transmitted through this single pivot point. The stresses involved were enormous. Yet here it was, not just functional but apparently reliable enough that American carriers could launch and recover aircraft at rates Japanese carriers couldn't match. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Nakamura ordered his team to take precise measurements of the pivot mechanism. They documented everything. The angle of the pivot axis, 63 degrees and 40 minutes from horizontal, 28 degrees and 30 minutes from vertical. The diameter of the pivot pin, the thickness of the mounting brackets, the way the control cables were routed through bell cranks that maintained aileron connection even as the wing folded. But as they worked, something became apparent that went beyond the mechanical cleverness of the folding system. The wing structure itself was unlike anything in Japanese aviation, where Japanese engineers had learned to shave grams from every component, building wings that were marvels of lightweight efficiency. The Hellcat's wings were built like bridge girders. "Look at this spar," one structural engineer called out. They'd removed access panels to examine the internal structure. The main wing spar, the backbone of the wing, was a massive I-beam of aluminum alloy. It ran from the fuselage out to the wing fold, and then another equally robust section continued from the fold to the wingtip. The spar's dimensions were staggering. Where a Zero's wing spar might be measured in millimeters of thickness, optimized for the minimum material needed to handle flight loads, this American spar was built with what looked like absurd redundancy. The flanges, the top and bottom sections of the I-beam, were thick enough to stop rifle rounds. The web, the vertical section connecting the flanges, wasn't a thin sheet barely adequate to resist buckling. It was a substantial piece of metal with ribs every few inches, providing additional reinforcement. "They're not designing for normal flight loads," Nakamura said, slowly as the implications settled over him. "They're designing for battle damage." It was a revelation that contradicted everything Japanese aeronautical engineering had been built upon. Japanese fighters were designed to avoid getting hit. Speed, maneuverability, the assumption that a skilled pilot could evade enemy fire. The entire Zero program had been built on that foundation. This American fighter was designed from the ground up with the assumption that it would get hit, probably multiple times, and would need to keep flying anyway. The engineers continued their examination over the following days, and each new discovery reinforced that initial assessment. The wing fold itself wasn't just a space-saving mechanism. It was part of an integrated structural system that gave the Hellcat redundancy Japanese fighters didn't possess. The wing was divided into 3 sections, the center section that remained fixed to the fuselage, and the 2 outer panels that folded back. This meant the aircraft had multiple structural paths for load transfer. If the outer wing took damage, the loads could still be transmitted through the center section and the opposite wing. If one wing's fold mechanism was damaged, the wing could theoretically be locked in place, and the aircraft could still operate, albeit with reduced performance. One engineer discovered that the fuel tanks were all located in the center wing section, inboard of the fold line. No fuel lines ran through the fold mechanism. No electrical systems crossed that pivot, except through carefully protected connections, designed to be disconnected when the wing folded. American pilots could land with battle damage to an outer wing panel, have that panel removed entirely, and theoretically fly the aircraft back to a repair depot with stubby wings, assuming they could manage the altered handling characteristics. "Count the rivets," Nakamura instructed. It seemed like busy work, but he wanted the numbers. A junior engineer spent 2 days doing exactly that, counting every rivet in the wing structure, measuring their spacing, their diameter, their pattern. The report was remarkable. The Hellcat's wing used nearly twice as many rivets as a comparable section of Zero wing. More than that, the rivet patterns showed deliberate redundancy. Where Japanese engineers used single rows of rivets to join structural members, the Hellcat used double and sometimes triple rows. Where Japanese practice was to space rivets as far apart as possible while still maintaining structural integrity, the American approach seemed to be to use more rivets than were strictly necessary for normal operations. "It's defensive engineering," one of the senior engineers concluded. "They're assuming that battle damage will destroy a percentage of these connections. They're building in enough redundancy that even with significant damage, enough rivets will remain intact to hold the structure together." The wing skin itself revealed similar philosophy. It was thicker than Japanese practice, heavy enough that it contributed to the structure rather than being merely a covering. When they examined the wing's internal structure more closely, they found that the ribs, the cross-sectional supports that gave the wing its aerodynamic shape, were spaced more closely than in Japanese aircraft. This meant that even if the skin was punctured, even if a shell exploded inside the wing, the structural loads could redistribute through the closely spaced ribs, rather than causing catastrophic failure. By the end of the first week, the team had compiled enough data to begin formal testing. They wanted to understand not just how the mechanism worked, but how strong it actually was. Could it really handle the loads that combat would impose? They constructed a test rig that allowed them to cycle the wing-fold mechanism repeatedly while measuring the forces involved. They folded and unfolded the wings 50 times, then 100, monitoring for signs of fatigue or wear. The mechanism showed minimal degradation. The pivot pin had been hardened to a degree that surprised the engineers. The mounting brackets were designed with factors of safety that Japanese engineers, working with limited materials, couldn't afford to replicate. "They're not worried about weight," one engineer observed, or rather, they've accepted that this aircraft will be heavy, and they've designed everything else around that reality. It was true. The Hellcat was a heavy fighter by anyone's standards. Empty, it weighed over 9,000 pounds. Combat loaded, it could exceed 13,000. The Zero weighed less than half that. But the Americans had the engine power to move all that weight. The Pratt & Whitney R2800 Double Wasp produced 2,000 horsepower, nearly double what the Zero's Sakai engine could manage. This revealed another aspect of the design philosophy. American engineers weren't trying to achieve superiority through elegance or efficiency. They were achieving it through brute force, backed by industrial capacity. The Hellcat wasn't a refined thoroughbred. It was a draft horse, powerful, reliable, able to absorb punishment that would kill a more delicate machine. The question that haunted Nakamura as the evaluation continued was whether the wing-fold mechanism itself contributed to the aircraft's legendary survivability, or whether it was merely incidental to the overall design. The answer came from an unexpected source. They received combat reports from a fighter group that had engaged Hellcats over the Marshall Islands. One of the surviving Japanese pilots had put sustained cannon fire into a Hellcat's wing right at the fold line. He'd seen his 20mm shells striking home, seen pieces flying off the American fighter. By every reasonable expectation, that wing should have failed. The structural discontinuity introduced by the fold mechanism should have been a weak point, a place where battle damage would cause catastrophic failure. The Hellcat had turned away trailing smoke, but it hadn't broken up. It had kept flying, made it back toward the American fleet. The Japanese pilot, low on fuel himself, hadn't been able to pursue and confirm the kill. But he was certain he'd hit the fold mechanism dead center with multiple cannon shells. Nakamura looked at the Hellcat's wing fold with new appreciation. "Bring me the structural drawings," he said. "I want to understand exactly how this pivot is designed." What they discovered was that the wing fold mechanism wasn't a weak point at all. In fact, it might be one of the strongest parts of the entire aircraft. The pivot pin was massive, machined from a single billet of high-strength steel. The mounting brackets that attached it to the wing spar and the fuselage were reinforced with multiple layers of aluminum. The entire assembly was over-engineered to a degree that seemed excessive until you realized what it meant in combat. If a shell struck the wing fold area, it would encounter so much structural metal that it might not penetrate completely. Even if it did, the redundant load paths meant the wing wouldn't immediately separate. The fold mechanism itself acted as a sort of structural armor, a concentration of metal at a critical junction that could absorb damage that would destroy a more conventional wing attachment. "They've turned a potential weakness into a strength," Nakamura said quietly. "The fold introduces complexity, yes, but that complexity provides redundancy. Multiple pivot points, multiple structural members, all working together. Any one of them can be damaged without causing total failure." There was more. As they examined the control systems, they discovered that the Hellcat's aileron controls were routed through the wing fold in a way that provided backup. If the primary control cable was severed, there were secondary connections that could maintain partial control. It wasn't elegant, it added weight and complexity, but it meant a pilot might maintain some control of a damaged aircraft instead of losing all aileron authority when a single cable was cut. The Japanese engineering team worked through July and into August, compiling their findings into a comprehensive technical report. The document grew to hundreds of pages, filled with measurements, photographs, stress calculations, and increasingly somber assessments of what they were facing. The Hellcat's wing fold mechanism represented everything about American naval aviation that Japan couldn't match. It was clever, yes, mechanically sophisticated in ways that commanded respect. But more than that, it was the product of an engineering philosophy that accepted weight and complexity as necessary costs to achieve survivability and operational flexibility. Japanese carriers couldn't achieve American launch and recovery rates partly because Japanese aircraft took longer to prepare for flight. Folding wings manually was time-consuming. The Hellcat's mechanism allowed 2 sailors to fold the wings in seconds, hydraulic assistance making it almost effortless. That speed multiplied across an entire carrier deck meant American ships could launch and recover aircraft faster, sustain higher sortie rates, maintain offensive pressure in ways Japanese carriers couldn't match. But the reports that truly disturbed Nakamura came from combat analysis. Japanese pilots were describing the psychological impact of fighting aircraft that seemed unkillable. Pour cannon fire into a Hellcat's wing, see pieces flying off, watch it smoke, and it would turn away and escape. The Zero had always relied on its weapons' ability to instantly destroy enemy aircraft. A few hits from the 20mm cannons would set an enemy fighter ablaze or cause it to disintegrate. Hellcat pilots were reporting taking multiple hits, making it home, and flying the same aircraft again days later after repairs. The structural strength isn't just about the wings, one engineer noted in his section of the report. It's the entire aircraft. The fuselage structure, the armor around the cockpit and engine, the self-sealing fuel tanks. They've designed a system where every component contributes to survivability. By September of 1944, the evaluation was complete. The captured Hellcat had revealed its secrets, but those secrets offered no easy solutions. Nakamura's final report to Naval Headquarters was honest to the point of being painful. The American F6F Hellcat represents a paradigm we cannot match with our current industrial capacity and design philosophy. The aircraft's survivability stems from redundant structural design, extensive use of armor, and engineering margins that assume battle damage rather than attempting to avoid it. The wing fold mechanism exemplifies this approach, a complex system that paradoxically increases reliability through its redundancy. To build an aircraft of similar capability would require, first, engines producing at least 2,000 horsepower, which we lack. Second, aluminum alloys in quantity. Third, accepting a weight penalty of approximately 3,000 kilograms over our current fighters, which would require new carrier designs to handle the increased deck loads. Fourth, a fundamental shift in design philosophy from performance optimization to survivability prioritization. None of these requirements can be met with available resources. The Hellcat is not simply a better aircraft, it is the product of an industrial system we cannot replicate. The report was received in silence by the officers who read it. By late 1944, everyone in the Naval Aviation Bureau knew the war was going badly. But seeing it spelled out in engineering terms, understanding that the problem wasn't just one of production volume, but of fundamental design, philosophy, and industrial capacity, made the situation brutally clear. The Hellcat, sitting in the hangar at Yokosuka, had taught its captors exactly why they were losing the air war. And that knowledge changed nothing. Understanding the problem didn't provide solutions when the solutions required resources Japan simply didn't have. The captured Hellcat remained at Yokosuka through the autumn of 1944, a silent monument to industrial disparity. While Nakamura's team had completed their initial evaluation, the aircraft became a training tool, a reference point for pilots and engineers trying to understand what they were facing in the Pacific skies. New pilots, those few who were still being rushed through abbreviated training programs, were brought to look at it. Instructors would walk them around the massive fighter, pointing out details that might save their lives. See the armor plating behind the pilot's seat? Your cannon shells will likely not penetrate it. Aim for the engine, the wings, anywhere but that protected cockpit area. But even as they spoke, the instructors knew the advice was nearly worthless. Getting into position to make a careful aimed shot against a Hellcat required advantages in speed or altitude that the Zero no longer possessed. By October, reports from the Philippines were describing aerial battles where the disparity had become overwhelming. At the Battle of Leyte Gulf, American carrier groups were launching hundreds of Hellcats while Japanese forces could barely scrape together enough aircraft to mount effective attacks. The captured Hellcat at Yokosuka represented not just technical superiority, but a glimpse into the American logistical system that was producing them. One of the engineers had calculated the numbers, doing the arithmetic that military planners preferred to avoid. Grumman's factory at Bethpage, Long Island, was producing approximately 12,000 Hellcats over a 30-month period. That worked out to roughly 400 aircraft per month from a single factory. For comparison, Japan's entire aircraft industry, all manufacturers combined, was producing approximately 1,500 aircraft per month total by late 1944, and that number was falling as strategic bombing intensified. But raw production numbers didn't tell the complete story. The Hellcat's design had been optimized for rapid production in ways that Japanese aircraft weren't. Nakamura had noted this during his evaluation. The Hellcat used standardized components, interchangeable parts, manufacturing techniques that prioritized assembly speed over craftsmanship. Look at the wing panel attachments, he'd pointed out to his team. They're using the same size bolts throughout. The access panels are standardized. The control surfaces use identical hinge designs. An American maintenance crew can swap parts between aircraft without custom fitting. They've accepted slightly less optimal aerodynamics in exchange for massive improvements in production speed and field maintenance. Japanese aircraft, by contrast, were still being built using techniques that required skilled craftsmen. Rivets were hand-set, panels were custom-fitted. Each aircraft was slightly different from the next, variations introduced during assembly that made spare parts interchangeability problematic. It was manufacturing philosophy from an earlier era, and it couldn't scale to meet the demands of industrial warfare. The wing fold mechanism itself exemplified this difference. It was a complex piece of engineering, yes, but it was designed to be manufactured in quantity. The pivot pins were lathe-turned, probably on automated machinery. The mounting brackets were stamped and then machined to final dimensions. Nothing required hand-fitting or careful adjustment. 2 sailors on a carrier deck could fold and unfold the wings without tools, without special training, because the mechanism was designed to be foolproof. Japanese engineers had tried to incorporate lessons from the Hellcat into new fighter designs, but the constraints were insurmountable. The Kawanishi N-1K Shiden, which was entering production in late 1944, represented Japan's attempt to build a Hellcat equivalent. It was more heavily armed than the Zero, better protected, more powerful, but it was also significantly more complex to manufacture, and production rates never reached the levels needed to impact the air war. By November, the strategic situation had deteriorated to the point where technical evaluations seemed almost academic. The Philippines were falling. American carriers were operating with impunity off the Japanese home islands. The Hellcats that had seemed like a solvable problem 18 months earlier had become an unstoppable force, one element of American air superiority that included Corsairs, Thunderbolts, and increasingly sophisticated tactics. But the captured Hellcat continued to offer lessons, darker ones now. Intelligence officers brought pilot interrogation reports to Yokosuka, asking engineers to evaluate specific claims. One report described a Hellcat that had sustained hits from multiple 20mm cannon shells along the wing fold line, exactly the scenario they'd tested in theory. The American pilot claimed the wing had been damaged but hadn't failed, allowing him to make it back to his carrier. Nakamura pulled out the structural analysis his team had done months earlier. "It's consistent with what we found," he said. "The fold mechanism creates a concentration of structural strength. Even with damage, enough load-bearing elements remain intact to prevent catastrophic failure." The officer listening to him was quiet for a moment. "Can we tell our pilots anything useful? Any weakness they can exploit?" "The landing gear," Nakamura said finally. "It's robust, but it's also complex. If they can damage the hydraulics, the Hellcat might not be able to lower its gear. That would force a belly landing on the carrier, which it would damage the aircraft significantly." He paused, "But getting a clear shot at the landing gear during aerial combat is nearly impossible. And even if you succeed, you've only ensured that one specific aircraft is out of action temporarily. The Americans will repair or replace it within days." What he didn't say, what both men understood, was that the problem wasn't finding tactical vulnerabilities in the Hellcat's design. The problem was that for every Hellcat they managed to shoot down, 3 more appeared to replace it. For every Japanese pilot who learned how to fight the Hellcat effectively, 2 died before they could pass on that knowledge. The attrition mathematics were unsolvable. December brought the first sustained American carrier raids against the Japanese home islands. Hellcats appeared over Tokyo, over Yokohama, flying top cover for bombing strikes with a confidence that spoke to complete air superiority. Air defense fighters that rose to meet them were swept aside. The handful of experienced Japanese pilots who remained could sometimes hold their own against individual Hellcats, but they were always outnumbered, always forced to break off and run when American formations massed against them. The captured Hellcat sat in its hangar while American Hellcats flew overhead. The irony wasn't lost on anyone at Yokosuka. They had the aircraft, understood its design, could measure and document every aspect of its construction. None of it mattered because the problem wasn't knowledge. The problem was industrial capacity, pilot training pipelines, resources, all the elements of modern warfare that Japan lacked and America possessed in overwhelming abundance. In January of 1945, American forces invaded Luzon in the Philippines, and the naval air battles around that campaign demonstrated just how complete American dominance had become. Japanese aircraft losses were catastrophic. American combat reports described shooting down formations of Cominterrelisas, Japanese aircraft that barely fought back, their pilots so inexperienced that they fell to the first burst of gunfire. A new batch of combat assessments arrived at Yokosuka, and Nakamura was asked to review them from an engineering perspective. One report caught his attention. An American pilot described putting more than 200 rounds of .50 caliber ammunition into a Japanese fighter, likely a Zero or an Oscar. The Japanese aircraft had caught fire immediately and gone down. The same pilot noted that 2 weeks earlier, he'd seen a Hellcat in his squadron take similar damage and make it back to the carrier. The pilot had counted over 70 holes in the Hellcat's airframe. 70 holes. Nakamura did the mathematics, assuming half-inch caliber projectiles that represented massive structural damage. Yet the Hellcat had remained controllable. He pulled out his structural analysis from the previous summer and reviewed the redundancy calculations. Even with 30% of the wing's rivets destroyed, even with multiple spar sections damaged, the structure would hold together under reduced G maneuvering. The pilot would have significant control limitations, but the aircraft would fly. "It's not just that they can build them faster than we can destroy them," he said to his assistant. "It's that we can't reliably destroy them at all. Our weapons are optimized for aircraft like ours, lightly built, dependent on every structural member. The Hellcat is designed to be partially destroyed and keep fighting." The assistant nodded slowly. "And every Hellcat that makes it home despite damage is an aircraft we have to fight again, while every Zero that takes comparable damage is gone forever." Along with its pilot, Nakamura added quietly, that was perhaps the cruelest arithmetic of all. American pilots bailed out over water and were rescued by destroyers, submarines, flying boats that risked enemy fire to pull downed aviators from the ocean. American pilot survival. Rates were extraordinary by Japanese standards. Japanese pilots who went down over water usually drowned or were never found. Every loss was permanent. The Hellcat contributed to that disparity. An American pilot could take battle damage, nurse his crippled fighter back toward the fleet, and ditch near friendly ships if the aircraft finally gave out. The rugged construction meant Hellcats could survive water landings that would shatter Japanese fighters. American pilots had a realistic chance of surviving even catastrophic damage. Japanese pilots flying Zeros knew that serious hits meant death. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. By February of 1945, the captured Hellcat's role had shifted again. It was no longer a mystery to be solved, but a benchmark against which Japanese designs were measured and found wanting. Engineers working on new fighter projects would visit Yokosuka, examine the American fighter, and return to their drawing boards with specifications they knew they couldn't meet. One young engineer, fresh from university, spent a week taking measurements for a new interceptor design his team was developing. He focused particularly on the wing structure and the fold mechanism, trying to understand if similar structural redundancy could be incorporated into a lighter airframe. "It's not possible," Nakamura told him when he presented his analysis. "The redundancy requires weight. The weight requires engine power. The engine power requires fuel. The fuel requires tankage, which requires more structure. It's a system, each element supporting the others. You can't extract the survivability element without addressing all the supporting requirements." "But surely there must be something we can learn," the young engineer protested. "Some principle we can apply?" Nakamura was quiet for a long moment. "The principle is simple," he said. "Finally. Build everything stronger than it needs to be for normal operations. Accept the weight penalty. Provide redundant systems. Use standardized parts. Optimize for field maintenance and rapid production rather than absolute performance. These are all things we've known for months. We simply lack the industrial capacity to implement them." The young engineer left deflated, his notebook full of measurements that would never translate into aircraft Japan could build. Nakamura watched him go and felt a familiar frustration. They'd learned everything the Hellcat had to teach. The problem was that learning didn't equal capability. March brought American carriers to within sight of the home islands for sustained operations. The Hellcat had evolved again, newer F6F variants with improved engines, refined aerodynamics, provisions for rockets and bombs. American fighters were increasingly being used as fighter bombers, attacking ground targets, supporting invasion forces, roles that the Zero had never been designed to fill adequately. The captured Hellcat, now nearly a year old in Japanese hands, was showing signs of age. The engineers had cycled its wing-fold mechanism hundreds of times during their testing. They'd removed and reinstalled access panels repeatedly. They'd examined every accessible component. Despite this examination, despite essentially disassembling and reassembling portions of the aircraft, it remained airworthy. An American maintenance crew could probably have it combat-ready within hours. That resilience, that ability to tolerate intensive examination and remain functional, was itself a lesson. Japanese aircraft were delicate, required careful handling, suffered degradation from rough field conditions. The Hellcat was built to be manhandled, to operate from carrier decks where space was limited and speed was essential, to survive not just combat damage but the daily abuse of military service. April of 1945 brought the invasion of Okinawa, and with it, the largest deployment of Hellcats of the entire war. American carriers operating off Okinawa were launching continuous patrols, maintaining air superiority over the invasion fleet and the surrounding seas. Japanese kamikaze attacks, the final desperate tactic of an air force that could no longer win through conventional means, were being intercepted by Hellcats flying combat air patrol. Reports filtered back to Yokosuka describing the aerial defense of the fleet. Hellcats were being used in new roles, as radar-equipped night fighters, as ground attack aircraft supporting marine advances, as fleet defense interceptors. The aircraft's versatility, its ability to fill multiple roles without major modifications, spoke to the fundamental soundness of the design. Nakamura received orders in late April to prepare a final comprehensive report on the captured Hellcat, incorporating all the lessons learned over the previous 10 months. The report was meant to inform future Japanese fighter development, though everyone involved understood the bitter truth that there would be no future Japanese fighter development of any significance. The war was being lost on every front. Strategic materials were scarce. Fuel was scarcer. The industrial infrastructure that would be needed to build a Hellcat equivalent was being destroyed by American bombing. He worked on the report through late April and into May, compiling a decade of Japanese aviation engineering experience into an honest assessment of why it had failed. The Hellcat wasn't the sole reason for Japanese defeat in the air war, but it was emblematic of all the reasons. It represented industrial capacity, pilot training systems, design philosophy, resource availability, all the elements where America had advantages Japan couldn't overcome. The section on the wing fold mechanism became, in his report, a case study in competing engineering philosophies. The Grumman Sto-Wing system achieves multiple objectives simultaneously, he wrote. It provides space savings on carrier decks, enabling higher aircraft density and faster operational tempo. It introduces structural redundancy that increases combat survivability. It uses standardized components that simplify production and maintenance. Most significantly, it reflects a design approach that accepts complexity and weight as acceptable costs to achieve operational advantages. Japanese aviation engineering has traditionally prioritized performance optimization, seeking maximum capability from minimum material. This approach produces aircraft of great elegance and, under ideal conditions, impressive capability. However, it creates fragility. Our aircraft perform superbly until damaged, at which point they fail catastrophically. We have built fighters for peacetime demonstrations, not for industrial warfare. The Hellcat, by contrast, is designed with the assumption of damage. Its structural members are overspecified. Its systems are redundant. It sacrifices theoretical maximum performance for practical operational reliability. In the conditions of actual combat, this philosophy has proven decisively superior. The report went on for hundreds of pages, each section documenting another way the Hellcat exceeded Japanese equivalents. Engine power, protective armor, ammunition capacity, radio equipment, oxygen systems for high-altitude operations, provision for external stores. In virtually every measurable category except low-speed maneuverability, the Hellcat was superior. And low-speed maneuverability had proven to be the least important performance characteristic in modern aerial combat. May brought Germany's surrender, and with it, the realization that Japan now faced the combined Allied powers alone. American industrial production was already being partially redirected toward Pacific operations. More carriers, more aircraft, more of everything. The captured Hellcat at Yokosuka represented what was coming, an endless stream of powerful, resilient, well-supported aircraft flown by increasingly experienced pilots. By June, the engineers at Yokosuka had moved on to other projects, analyzing B-29 bomber wreckage, trying to develop countermeasures for the firebombing campaign that was burning Japanese cities. The Hellcat sat in its hangar, largely forgotten, its lessons learned and filed away in reports that fewer people were reading as the strategic situation became increasingly desperate. Nakamura was reassigned to air defense planning, a role that involved trying to optimize the use of dwindling fighter resources against overwhelming American air superiority. He found himself returning occasionally to the Hellcat, walking around it in the quiet hangar, thinking about paths not taken. If Japan had prioritized pilot survivability over maneuverability back in the 1930s, would it have mattered? If Japanese carriers had been designed with larger deck elevators to handle heavier aircraft, if engine development had focused on power over weight savings, If industrial planning had emphasized production volume over craftsmanship, would the outcome have been different? He suspected not. The problems were too fundamental, the resource disparities too vast. Even if Japan had built perfect copies of the Hellcat, they couldn't have produced them in sufficient numbers, couldn't have trained enough pilots to fly them effectively, and couldn't have maintained the fuel supply to keep them operational. The Hellcat's superiority stemmed not just from its design, but from the entire industrial and military system that supported it. July brought preliminary indications that the war might be nearing its end. The Soviet Union was preparing to enter the war against Japan. Atomic weapons, though Nakamura didn't know about them yet, were being prepared for use. The captured Hellcat at Yokosuka sat through the final weeks of the war as American aircraft flew overhead daily, unchallenged, the air defense fighters that might have risen to meet them grounded for lack of fuel. On the 15th of August, 1945, Emperor Hirohito announced Japan's surrender. The war was over. The Hellcat had outlasted the Japanese Empire. American occupation forces arrived at Yokosuka Naval Arsenal in late August. Among them were intelligence officers and aviation experts tasked with cataloguing captured equipment and assessing Japanese technological capabilities. They found the Hellcat in its hangar, surrounded by Japanese technical documentation, photographs, disassembled components carefully labeled and stored. The American officers were bemused. Here was one of their own fighters, painstakingly analyzed by enemy engineers who'd clearly spent months trying to understand its design. The Japanese technical reports were remarkably thorough, showing an understanding of the Hellcat's construction that rivaled Grumman's own engineering documentation. They knew exactly what they were up against, one American aviation engineer commented after reviewing the reports. These assessments are professional, accurate, honest about capabilities and limitations. They understood the aircraft better than some of our own maintenance crews. What struck him most was the tone of the Japanese reports. No propaganda, no dismissive assessment of enemy capabilities, no comforting lies about how Japanese engineering was superior. Just cold professional analysis, acknowledging that the Hellcat represented a paradigm shift in fighter design that Japan couldn't match. The captured Hellcat was eventually shipped back to the United States, where it spent years in storage before being restored and placed in a museum. It still exists today, painted in American markings with no external indication of its time in Japanese hands. But in archives, the Japanese technical reports remain, hundreds of pages documenting how enemy engineers had examined this single aircraft and understood from it exactly why they were losing the war. The wing fold mechanism that had seemed so promising as an engineering curiosity became, in their analysis, a symbol of everything Japan lacked. It represented industrial capacity to build complex mechanisms at scale. It represented a design philosophy that prioritized practical operational advantages over theoretical performance optimization. It represented the ability to train average pilots to fly sophisticated aircraft safely because the aircraft were designed to be forgiving rather than demanding peak skill for basic operations. Most of all, it represented the assumption of survival. American engineers designed the Hellcat, expecting that pilots would take damage, would need to nurse crippled aircraft back to carriers, would ditch at sea and need to be rescued. Japanese engineering had been built on the assumption that skilled pilots wouldn't get hit, that if they did get hit seriously they would die, and that this was acceptable because skill and spirit could overcome material disadvantages. The Pacific War proved that assumption catastrophically wrong. The Hellcat's 19-to-1 kill ratio wasn't just about the aircraft's capabilities. It was about pilot survivability, about training systems that could produce adequate pilots in large numbers rather than excellent pilots in small numbers, about maintenance practices that kept aircraft operational, about industrial systems that could replace losses faster than they accumulated. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.